I am excited to be here to discuss a novel research field that is emerging in the intersection of two advanced technologies, computer vision and telecommunications, which is particularly interesting as we step into the era of 6G. As we start this presentation, it is critical to understand how the integration of these two fields is not just a technology advancement, but a paradigm shift that promises to redefine how we interact with our environment and also each other. Hello everyone, my name is Miguel Bordallo Lopez and I am Associate Professor at the Center for Machine Vision and Signal Analysis. Also, as a member of the 6G flagship, I lead the Strategic Research Area 3 that focuses in distributed intelligence. The 6G era will bring the convergence of computer vision and telecommunications. I would like to start by showing some groundbreaking future opportunities and the potential that lies in the intersection of these two dynamic fields. The sixth generation of communication isn't just about faster speeds or broader bandwidths. It is about enabling a level of communication and visual interaction that has been previously unimaginable. Imagine a world where your devices don't just see or communicate. They understand and interact with the environment in ways that profoundly augment our daily experiences. In this context, vision and communications can and will be developed in a joint manner. Multiple technologic paradigms and application scenarios will emerge from this research. By developing both fields together, new technological concepts such as radio-based remote sensing or video-radio digital twins can easily become prevalent. Think of, for example, security applications or smart manufacturing, autonomous robots and vehicles, smart traffic, remote monitoring, assistive living, safety and wellness. All of the sectors will be impacted. In this presentation, we'll discuss the evolution of these fields, the opportunities this convergence brings, and how together they will open the way for future innovation. So, let's begin. To understand the current developments, it's crucial to know about the distinct paths that both telecommunications and computer vision have traversed over the years. So these fields each have its own rich history, and they have evolved through groundbreaking innovations and paradigm shifts. However, both computer vision and telecommunications have been, during decades, evolving separately. Telecommunications is a field that has revolutionized human connectivity, and it has come a long way. From the early days of first generation of mobile communications, we have progressed to 5G and beyond. And now we can see ubiquitous access to internet and high-speed mobile communications. We could say that each era has seen a leap in how we connect and communicate over distances. At the same time, computer vision has been on a remarkable journey. Computer vision began with the ambitious idea to enable machines to see and interpret the world. This has now become a reality. The field has evolved from simple image processing and recognition of geometrical forms, letters and numbers, to sophisticated systems capable of facial recognition, object detection, 3D reconstruction, and world segmentation. The most recent developments aim at creating vision foundation models, something that put them close to being able to model our whole world and perform decision-making based on that. However, today, these two fields should not be considered completely separated, since it's obvious that some of the characteristics of these two fields are converging. Both fields are facing problems with the same application scenarios, such as localization, sensing, distributed computing, and increased intelligence. Many of these problems should be tackled together. The once separate paths of distant communication and machine vision are now intertwining. As we look in the convergence of computer vision and telecommunication, it's essential to understand the vast array of opportunities this union unlocks. The fusion of these two fields is not just about combining two technologies, it's about creating new capabilities that were previously unconceivable. This convergence is opening doors to innovations that promise to enhance how we interact with our surroundings and access information. Imagine the potential of leveraging computer vision to enhance wireless communication networks. By integrating visual data, we can significantly improve the accuracy and efficiency of wireless transmissions, foresee and adapt to environmental changes, and even anticipate and resolve potential network issues before they impact users. Similarly, the advanced capabilities of 6G networks can dramatically enhance computer vision applications. Enhanced speed and reduced latency of 6G will allow for real-time processing of complex visual data, enabling more sophisticated and responsive vision-based systems. Although we are talking on a complementary technology that can work in tandem with traditional signal processing, this convergence is not just a technical enhancement, it's a transformative shift that will impact various industrial and economic sectors. To understand the specific of this convergence, I want to focus on a pivotal concept, a new paradigm, the concept of view to communicate. The idea is at the heart of how computer vision can assist telecommunications in the 6G era. The term view to communicate encapsulates how visual data captured through computer vision can inform and significantly enhance telecommunication strategies. It is about using the power of visual insights to drive communication technologies forward. In a world where data is increasingly important, the visual information provides a rich, contextual layer that telecommunication networks can and should leverage. This concept represents a profound synergy between two domains. By incorporating visual data to recognize the context and the characteristics of the environment, we can not only refine channel estimation and network coverage, but we can also proactively address signal blockages and adapt communication strategies to fit the complex real-world environments and use tailored solutions. We are enabling these networks to understand and interact with their environment in a much more nuanced and sophisticated way, and enabling new possibilities such as effective non-line-of-sight communications, faster beamforming convergence with learning schemes. The potential impact on all types of network applications will be very noticeable, as they can, for example, be enhanced with preemptive adaptation and decision-making. We will now explore some specific examples on how View to Communicate is being implemented to predict wireless channel dynamics and to aid in the creation of 3D environment maps, showcasing the practical implications of this convergence. Let's see an example application of this View to Communicate paradigm. In this example, we focus on predicting wireless dynamics through vision. The aspect is where the convergent power of computer vision becomes a game changer for telecommunications in 6G. With the deployment of 6G, the accuracy of wireless communications becomes even more critical. Computer vision provides us with the ability to not just see but interpret the environment. It can observe physical barriers, understand movement patterns, and predict changes that could affect signal transmission. Imagine cameras in urban areas that continuously gather data. This data can become a predictive tool, allowing us to detect potential signal blockages in real time. This could be from everyday things such as construction work of a new building or a parade moving down the street. In this context, by analyzing camera data, our systems can anticipate when a large vehicle is about to obstruct a signal path or when a new construction could lead to long-term changes in network topology. This foresight allows for dynamic adjustments to be made, ensuring more consistent and reliable communication. Visual data could then be translated into predictive models. This model might help us navigate the complex dynamics of wireless channels, ensuring that 6G networks are not just fast and efficient, but also intelligent and adaptive to their surroundings. It has to be noted that adaptive network coverage can be implemented, especially in crowded areas, using not only base stations, but also leveraging, for example, user Wi-Fi routers or other vision-equipped devices. The main point is that computer vision can transform the reactive nature of current network management into a proactive one, so that the networks are not only fast, but also smart. In order to fully exploit the View to Communicate paradigm, we should focus on a critical component, which is the creation of dynamic 3D maps for vision radio simulation. Millimeter wave signals are highly reflective. Due to this, in this case, 3D mapping becomes more than just a representation. It is an essential prerequisite for accurate communication in 6G networks. These detailed maps are not just static images, but dynamic models that adapt to the ever-changing environment, enabling precise simulation of complex indoor and urban landscapes. Luckily, we can still use the same advanced cameras and communication devices to capture both rich visual data and the electromagnetic properties of the materials. When combining this visual information with radio data, it provides a comprehensive understanding of environmental dynamics. These maps can include also those critical non-line-of-sight elements that traditional methods might miss. This integration of multimodal information in the mapping process is very important for simulating telecommunications strategies. Simulation allows us to design networks that are not only efficient, but also resilient to thousands of physical changes that occur in real-world environments, ranging from new construction to daily traffic patterns. Take, for example, the 3D campus map that is created with Azure Kinect technology that I'm showing here in the slides. It illustrates the level of detail and scale that we can achieve, which is a powerful tool for planning our smart cities. On the screen, you can see the technologies that contribute to this process, from multi-view stereo to LiDAR, from SLAM to RGB sensors. Each sensor modality can play a different role in constructing these models, which are foundational to the vision radio simulators that will drive the future of 6G communications. Traditionally, acquiring such large-scale models has been costly and slow. However, the development of new algorithms, communications, and computation capabilities allows now capturing denser and more accurate point clouds faster than ever before, which can be directly utilized in ray tracing and simulation of communication paths and signals. This progress is not incremental. It can be revolutionary since it enables us to envision telecommunication with unprecedented precision. We can also consider the opposite concept, the communicate-to-view paradigm. This explores the interesting dynamic where telecommunications not only facilitate but actively enhance computer vision capabilities. Communicate-to-view is a concept where the robust data capabilities of telecommunications, especially within the 5G and 6G spectrum, are utilized to significantly aid and refine vision tasks. This relationship allows for a richer, more detailed understanding of the visual world. Telecommunication data can provide approximate distance priors that can be useful in monocular depth estimation, crucial for understanding the dimensions and spatial relationships within a scene. In the small video on the corner, it can be seen how just a small number of distant points measured on the environment dramatically improve 3D reconstruction from single images. Moreover, radio data could also aid in the reconstruction of novel views from incomplete data, offering perspective that a single camera alone could not achieve. At the same time, the advanced network provided by 6G bring an unprecedented level of detail and speed to this process. They allow for a seamless fusion of communication and vision using low latency, high-speed transmission of visual information, enabling real-time enhancements and interpretations that were previously not possible. As you can see in the diagrams shown here, the integration of telecommunication data into vision tasks is not just additive, it is transformative. It allows computer vision systems to transcend traditional limitations, offering a depth and versatility to applications ranging from augmented reality to autonomous navigation. I can show you now an example on how the communicate-to-view paradigm augments our vision and increases our situational awareness by, for example, providing us with the ability to extend our vision beyond direct line of sight. Essentially, the combination of communication devices and cameras will allow us to see around the corners. Utilizing the capabilities of 6G, millimeter wave sensing has the extraordinary ability to perceive the environment by detecting how moving objects affect signal propagation. This technology takes advantage on the particular way that millimeter wave signals reflect and scatter off the surfaces and objects, providing us with information about what lies beyond our immediate visual field. This is, for example, similar to our human ability to sense the presence of someone that is approaching from around the corner by just observing the subtle changes in the light and shadow. However, this technology does not need to be limited to passive observation. It actively interprets the environment and adapts to maximize signal perturbations to offer enhanced situational awareness. It can be a proactive form of sensing, constantly adapting and learning from the environment to enhance real-time visual information. The image here shows how millimeter wave sensing can perceive these objects. Through simulations, we can see the practical application of this technology as it translates complex signal interactions into a comprehensible visual format, in combination, for example, with 3D maps or with generative computer vision models, which enables us to effectively view around the corners. This has profound implications. For example, autonomous vehicles could be able to detect a pedestrian around a blind corner. Emergency services could be able to locate people in obscure areas and maybe even read their biosignals and vital signs from a distance. The potential applications are vitally important. A complementary scenario in the communicate-to-view paradigm is the concept of distributed sensing, which essentially could allow us to see through walls or across the distances. Seeing through walls is a powerful metaphor for the advanced capabilities that high-speed and ultra-reliable communications can bring to vision tasks. Distributed sensing allows us to extend our visual reach, breaking through the constraints of physical barriers, and gaining a new level of situational awareness. Through the integration of millimeter wave sensing with mobile devices and strategically placed cameras, we are not just capturing images, but leveraging a fabric of visual information that allows us to see not only from another point of view, but also beyond the visible spectrum. This allows for real-time awareness and a comprehensive understanding of the local information, even of the information that is hidden from the naked eye. Consider just this practical scenario. Let's imagine a network and sensors of cameras, where each one is actually a node in a CC network, and these cameras can provide seamless and almost complete visual coverage of the scene. As a user, as you move from room to room, from space to space, from street to street, wherever that is your device can seamlessly connect to the nearest cameras and sensors, even those that go beyond the visible information. This can ensure that your view of the world is continuous and unobstructed, even if walls stand in the way. Paired with advanced 3D mapping and sophisticated visualization techniques, this seamless connectivity could allow us to access otherwise invisible information. This could be things as, for example, radio coverage, temperature maps, or even air quality. The graphic here showcases a distributed sensing network and illustrates how a 6G-enabled system could link and register both spatially and temporally multiple visual data points, creating a cohesive and uninterrupted visual experience. We have seen how this convergence of vision and communications could operate, but at the moment we are just at the beginning of a future full of potential. This means that there is still much work to do in different research areas, where development tasks and implementation challenges still remain. In the near term, the research should focus on refining the symbiosis between 6G communications and computer vision. This includes enhancing the spatial intelligence of devices, improving the accuracy of 3D environmental mapping, and developing algorithms that can effectively interpret complex multimodal data in real time. In this context, I think that the first step is to develop a set of tools that allows the experimentation on these paradigms. These include vision-enhanced communication devices such as user equipment, base stations, or even large reconfigurable intelligence surfaces. Simulating tools like radio vision ray tracing simulators, autonomous and distributed sensing and camera networks, or particularly specifically tailored machine learning algorithms for multimodal fusion and distributed sensing. All of these areas pose significant challenges on their own, while the seamless integration of these multimodal technologies poses a complex task, demanding advancements in computational efficiency, data transmission protocols, and energy management. In addition, the ethical and sustainability implications of these powerful, ubiquitous systems also present critical challenges that must be navigated with care. In the near future, as the practical implementation of this technology starts to emerge and develop, we can expect different transformations on how we understand these fields. As we discuss the convergence of vision and communications, it's clear that its impact will be felt across multiple sectors. We can try to consider how this technological union can impact different industry sectors, from automotive to healthcare, manufacturing, and logistics. For example, in the automotive industry, the integration of advanced sensors and communication systems is leading to safer and more efficient vehicles. It's envisioned that cars will also communicate with each other, and they will map the environment on their own based on vision sensors. However, we could also understand the impact of systems that would be able to map the environment using distributed sensors beyond their line of sight under view, and how it could essentially improve the reasoning while, for example, driving or flying. In healthcare, the combination of precise imaging and real-time data transmission could revolutionize diagnosis and treatment, and the ability to transmit high-resolution medical images instantly will enhance remote diagnosis and making specialist care more accessible even in remote areas. The ultra-densification of cameras and sensors can, however, move the burden of health monitoring from the patient to the environment itself. In manufacturing, the convergence will enable smarter factories. These factories will not just be automated. They will be deeply integrated systems capable of self-optimization. Sensors will monitor every aspect of the production line, as they will be able to work in a decentralized manner, but also be able to communicate with each other, maximizing efficiency and reducing downtime. Each sector will experience its own unique benefits from this technological convergence, and finding suitable use cases is now a very important research matter. We have discussed the upcoming convergence of vision and communication systems, including the paradigms of view to communicate and communicate to view. We haven't covered how these concepts are not merely technological advancements, but can potentially challenge how technologies are developed and how we will interact with the world. This convergence is more than the sum of its parts. The convergence of computer vision and telecommunications represents important ground for research and innovation. Looking ahead, our research must navigate the complex interplay of high-frequency bands like millimeter wave and the detailed data they can provide for both vision and communication tasks. The challenges are still substantial, and they range from the technical to the ethical, as they require extensive international and intersectional collaborations, including academic and industrial partners. As we stand on the beginning of this convergence, we are not just looking at faster networks, clearer images, or better object recognition systems. We are actually envisioning a new field of research that encompasses and fuses two worlds that were traditionally separated. This is the promise of the future that we've discussed today. And this concludes my presentation, and if you want to learn the details on the specific and technological foundations of the convergence of vision and telecommunications, please stay tuned for other 6E talks focusing on ray tracing for radio signals or radio-based sensing. And if you have any question, please contact me in the email shown on the slide. Thank you very much for watching.